Okay, welcome everybody. So today we're going to talk about how we can figure out where the CPU time is going in a program, because an engineering truism is you cannot improve what you cannot measure. So if we want to make a program faster, we have to figure out how we're going to measure where the time is currently going. And we're doing this in C++. So some of the techniques we're talking about are going to be applicable to all programming languages. I guess pretty much all of them are, but the exact tools we'll show you are for C++. Okay, so what's your current toolbox? What do you know how to do? You know big O analysis, and that's an important technique. It's part of what tends to differentiate, you know, computer engineers who are trained in a university in a rigorous program like you are versus people who are self-taught programmers. You can analyze the complexity of various data structures and algorithms and figure out which ones are going to be faster as the problem gets big. So you know that order n squared is bad, order n log n is much better, especially if n can get big. And the C++ standard library provides this complexity for most of the functions that you can call in it and the data structures. So you can, by looking up what is the complexity of this data structure, and you look at how many loops you have and how you use it, you can work out the overall complexity of various functions and algorithms, and you can tell this looks bad. Okay. You can also, you've learned some ability to look at code and guess, is this code fast or slow? So you can, in 244, for example, you learned about copy constructors. So when are you behind the scenes doing large copies? And that's a way you can speed up code. Get rid of a lot of big copies. Maybe we should pass this thing by reference instead, and it could be faster. It's not going to change the, well, sometimes that even does change the order of the algorithm, but that's a useful thing to do. So code inspection, looking for things like copies that can slow you down. You can guess based on what you think you know. So you just look at the code and you have a feeling. This is commonly done, but it's not a great practice because computers are complicated, right? How they run your code, what a compiler does to your code is complicated. Large programs are complicated. So your guessing is often wrong, and you may be optimizing the wrong thing. Sometimes you're even de-optimizing. You're making stuff work. And you can time your program by just starting up a stopwatch on your phone. So you can only time kind of relatively long operations, but you can do that right now. Okay, so these are all useful things. And this is the quote I just gave you. If you can't measure it, you cannot improve it. So we want to be able to measure and want to measure more than those previous techniques that I just talked about. So how are we going to do this? So there are a few different techniques you can use to measure the performance of your code. First one is you can do manual measurements. So manual measurements means you're going to write code. So you're going to add some extra code that measures time. The advantage of this is it's the lowest overhead. If you do this correctly, it doesn't change the behavior of your code much. It doesn't slow it down much. So that's good. And it can measure exactly what you want because you can choose where to put the timers. You can measure even parts of a function, so you can get very fine-grained timing. Disadvantage is you have to write code. Okay, so I didn't write this down as a disadvantage, but there's some work. And if you don't know where to start, you might not know where should I even write this code to start timing things. Another technique you can use is to sample using the debugger. So I'm going to show you this, but the debugger has pause and continue buttons. So by hitting those buttons, you can coarsely sample. You can only hit those buttons maybe once a second, or maybe if you're really fast, maybe a couple times a second. So you can get a coarse sample of where does the program spend its runtime. Where are you this second? Where are you the next second? Gives you an idea. And maybe that idea now helps you figure out where should I go write some code to see more information. And we can also use what's called a profiler. So a profiler, basically, I'll show you this in a few minutes, but basically a profiler automatically does what you're doing by hand when you do this pause and continue. It interrupts your program about 100 times a second and records where is it. And it does that throughout the execution of your program, and it keeps track of where were you every time I interrupted you. And then it summarizes that data to say you spent this long in this function, you spent this long in that function. There is some overhead. Okay, so the profiler is going to interrupt your program at some rate. Usually it's about 100 times a second. And during that interrupt, it's going to measure some things. So it's going to say, what function are you in? It's going to look at the call stack to see how did you get here, and it's going to record that information. And at the end of execution, that information can be summarized, and you can see how long did you spend in certain routines? How did you get to those routines? It will change the runtime of your program somewhat, because interrupting your program 100 times a second and gathering this data is going to add some CPU time. So is a little bit of a disturbance to the program when you turn on profiling, whereas this technique, sampling using the debugger, doesn't disturb your program at all, and writing code that times exactly what you want disturbs it very little. Okay, so let's start with the first one of those techniques, measuring performance manually. So the way you do this is you get a timestamp. There's a function that, well, there are multiple functions, but I'm going to show you a good one to call, that allows you to get the current time. All computers and all cell phones, every computer system has a clock in it. So we can ask, what's the time right now? And we do that before the region of interest, so before the code we're trying to time. Then we can go through that code. So maybe it's a big set of loops, maybe it's load map, and we can get the timestamp after that region of interest, subtract the before time from the after time, and that tells us how long did it take to go through that region of interest. Maybe it's load map. And then we can save that, we can output it, and we can output it in different units. Seconds, nanoseconds, milliseconds. I usually just do seconds because it's easiest to understand if I always output everything in seconds. Okay, so let me show you a little bit of sample code for that, and then I'm going to show you a slightly more complicated example on the actual milestone 2 code for our reference solution. So let's say I'm worried about the performance of my act on button press callback. And remember, we had this function, act on button press, that we worked on last week that we used, and I haven't shown the exact right function prototype here. I'll fix that after. But the act on button press routine, remember, was given an X and a Y of where the person clicked and figured out the latitude and longitude that corresponded to that. And then we called find closest intersection to figure out what is the ID of the intersection that they just clicked on. And right now I'm just going to print out what is that ID rather than highlighting that intersection and so on. And let's say I'm worried about the speed of this routine, because this find closest intersection, the way I coded it was order in. I looked through all of the intersections, so I'm a little worried this might be slow. So how am I going to time this? So the first thing I do is I include the chrono library. That's C++'s time library. The first thing I need to do, after that, I need to get the timestamp before the region of interest. And I can do that with just one call. So I'm going to get a start time. And chrono returns a time object. I don't really care exactly what that type is. I'm just going to use auto to say whatever this function returns, make me a variable of the right time to store it. So I call inside the standard library, inside the chrono namespace, a function called high resolution clock, an object called high resolution clock, and I'm calling a function called now. So long sequence of identifiers, but it in the end just calls this function called now. And that returns an object that represents the current time. Now I do my actual work. So I've kept the latitude, the longitude, and I do this order n calculation to find the closest intersection. And now I want to see how long it took. So I get the timestamp after the region of interest. So I just do the same code again. I basically say, give me the time now, and I'll store that in a new object, end. I can calculate the time difference by just subtracting those two things. So I take the end time minus the start time, that gives me the time difference. This is another time object. So it's not clear exactly what's in that. It's whatever chrono wanted to put in it. So I'm going to cast that using this funky bit of code. So something called it's basically another function inside of chrono that is going to convert that time object into seconds. So after I've done that, I've got a time that I can actually interpret. It's in seconds, and I'm going to print it out. So I just print out a little message that includes the time this took, and that's done by taking this duration object and printing out calling its count member function, which basically prints the time in seconds. Okay, so Chrono uses a kind of long syntax for certain things, but this sample code just shows you how to work with Chrono. You just use this exact code, it'll work fine. Okay, so that printed it out to the standard output. When I'm running my program, that might get inconvenient to just have it printing all sorts of stuff to standard output. So I'm going to save it to a file instead. So could do this if I only want one time measurement. I'm just worried about this one function. I want to quickly check it. But if I want more detail, probably better to save to a file. Okay, so what I'm going to add, well, I've still got my Chrono library that I'm going to use, and I'm going to add fstream. Fstream is file stream, so it allows me to read and write from files. And the first thing I'm going to do is I made lots of ways to do this, but the way I've chosen to do it is I've made a global variable here. It's of type in the standard library output file stream. So means it's a file that I'm going to send data to. I'm outputting to it. It's a stream, meaning I can use my stream operators just like cout. And it's a file. Okay, so I can write to it just like it's cout using exactly the same techniques that I've used before, but it's going to go to a file. I give it a name. So I'm going to call the object that I use to access that file perf. And the constructor for this takes the name of the file on disk. So I'm going to make a file called actonbuttonpress.csv. And .csv, you're probably familiar with. Does everybody know what a CSV file is? Anyone know what it is? What does CSV usually, what does that extension usually denote? Yeah, comma separated variables or comma separated values. So it's a simple format where you have a bunch of data in it separated by commas, and spreadsheet tools like Excel or the LibreOffice on the UG machines can open it. Okay, so I've created this file, and this constructor will open this file. If the file already exists, it'll discard any data that's in it. Okay, so I've already opened this, all right? And now I'm gonna make a little function that's a nice utility function, okay? So my profile CSV file, or I'm making a function called profile CSV. And this function, I'm passing in a start time, and I'm passing in a string. And that string is going to represent the name of a function. So it could be anything, but the way I intend for this profile CSV file to be, or function to be used, is I pass it in a starting time, and I pass it in the name of the function that I'm trying to time right now. And inside this function, I've basically just say get the end time. The end time is whatever the time now is. Compute the elapsed time, which just is end time minus start time, and cast it to this duration object, and then write out to this profile CSV file, okay? The function name that you passed in and the elapsed time that I just got from Chrono, and a new line, okay? So that's what it's going to print, all right? And I think I've got a little mistake here. So I'm going to go back and check this perf file name, and it should actually be profile CSV file. Okay, so I've got to basically make this file name match. So I'll fix that afterwards. But I didn't actually use a consistent file name here. If you're wondering what's going on, where did this profile CSV file come from? It should have really been this variable here. So we've got a file that we open up, and I've opened it up as a global variable, so I don't actually need to open that in load map. And now I can write to it. Okay, in Acton button press, I already showed you how to time it. With this new function, basically my timing looks even shorter. I get the start time by calling now, all right, and I save that in a variable start time. And now what I need to do at the end of this function is all wrapped up in this nice helper function. So it is called profile CSV. I pass it the starting time, right, which I got here. And I pass it the name of the function, like whatever I want printed to my CSV value. And then if I go up here, I'll see, okay, what does it do? It just gets the end time and it prints out how much time did the function take. So I'm basically just using this helper function to clean up some code. If I didn't have this helper function, I would have had to write a bunch of lines of code down here. I don't want to do that. By making this helper function, my profiling code looks simpler. Okay. How do you open a file again? There are multiple ways to do it. There's a member function called, I have to go look at it, but I think it's .open in C++. But also this constructor will open a file for you too. So in this particular case, this constructor is going to open up the file. So I don't have to do anything else. Does that answer your question? And because it's a global variable, the file will actually be closed at the end of the program automatically. Basically, when it calls this destructor, that closes the file. So this is a really simple way to open a file that I'd like to write to from all over the place. I made a global variable. The constructor is going to open the file and create it. If it's already there, this particular output file stream is going to get rid of the current contents. So I'm going to have an empty open file at the start of the program. At the end of the program, this is a global variable, and its destructor will be called. The destructor for this is actually going to close the file. Okay. The helper function. So let me erase some of this stuff because I got lots of stuff all over here. The helper function is this profile CSV file or profile CSV function. So I wrote a little helper function here, and all it does is it gets the current time. It was passed in a start time, so it goes, okay, I'm going to compute the difference between start time and the current time, and you passed me a string. I'm going to print that string, which we're saying should be the name of the function. I'm going to print that string and print the elapsed time to this comma-separated value file, which should already be open. Okay? So not very many lines in this, but I want to keep, because I plan to do this profiling in many functions, I want to keep the code I have to write really short. So I make a helper function so that I don't have to write 3 or 4 lines at the end of every function. I just have to add this line at the start of a function and this line at the end of a function in order to time it. Does that make sense? There's one other thing here. I put in this if-def profiling. Okay, so what this means is somewhere in my code, in a header file that everybody includes, maybe M1, well, let's say M2.h, or at the top of a C++ file, I'm going to have to, in order for this to actually get compiled in, I have to define profiling. Okay, so I have to basically say that what's called a preprocessor definition is defined. And now this code will be compiled in. If I don't do that, say I comment that line out of my code, or I just don't put it in at the top of the C++ file or some header file, then this code basically gets removed, right? The compiler will not process this code. It will not go in your program. That's actually useful because it means I can turn all of this profiling code that's generating a comma-separated value file on and off with one define, okay? So one line of code that I comment in or comment out turns on and off all this output. And that's a good way to do it because maybe in my final submission, I don't want the profiling output on. Okay, so does it make sense to everybody? If we put this in, and we do it for a whole bunch of different functions. So I showed you how you could use this for one function, the act on button press function. But if we put this in our program for all sorts of functions, then we'll get a comma separated value file, which is, let's see, this profile CSV file that looks like that. Oops. Okay, so it's basically a whole bunch of function names and the time that it took when that function was called. So draw all features, in this case, took 0.09 seconds. Act on button press took 29 seconds. So that was really long. So that sounds like maybe I got some slow code and so on. Okay, so let me show you a demo of this because that's probably the best way to understand this. You've seen now the basics of how this code works. Let me go and show you it on a more significant example. Okay, Abid, can you see my code screen now?
Yes.
All right, let me make this a little bigger. Okay, so this is actually this is actually our golden solution. So this is our reference solution. And let me show you the code that, let's see where I opened this file, because there was a question on that. Let's see. I want to show you all the code in here. Okay, let's see. So what I've done here is this. I told you that in order to turn this on, I need to define profiling, given the way I wrote it. Okay, so in one header file that I'm including all over the place, I define profiling. So if I wanted to turn this off, now I have one place to comment it out. So that's good. And let's see. In load map, here's where I'm actually opening the file. Okay, so in this particular example, I'm loading this profile CSV file here, or opening it here. So I call .open. Let me actually go to its definition to see what this is. All right, so this is a global variable. All right, profile CSV file, so that I can get it from everywhere. And in this particular case, instead of opening it right at program startup by putting the name of the file in the constructor, I explicitly open it by calling the open member function. And it's going to open a file called funcperformance.csv. All right. So let's see what else we have here. In load map, this is one of the functions I'm going to time. So I get the start time here. So this line is getting the start time. And if I go through to the very end of load map, you'll see that at the end of load map, I have that little bit of code. Well, I close the file there. Okay, so in this example, I'm not relying on the global variable open and close. I'm just doing it myself. And so I'm doing it in close map. And I have this function that I call at the end of any subroutine I want to time. So profile CSV, I call and I say, I pass in the starting time for this function and I pass in the name of the function. Okay, so let's go look at that function. It's going to look just like what I had before. So profile CSV, I showed you this on the lecture slides. Takes a start time that's passed in. So that's right here. It gets the current time. It works out the difference and it prints out to this file that should already be open. And in our reference solution, we open it in load map and close it in close map. And we print out the elapsed time as well as the function name that was passed in. Okay, so this func name is nothing magic. It's just a string that we passed in to say what are we currently timing. All right, so let me go back to, so what I just showed you is some of the small amount of infrastructure code to make this work and the fact that we're timing load map. This is our main screen redrawing routine, and that's what I'm going to mostly be timing in the next little while. Okay, so it's a screen redrawing routine. We called it draw. At the start of the routine, we get the current time. So there's our start time again. And then it goes through. I can actually slow this down. So I basically have wrapped a loop around our redrawing so I can have it redraw multiple times. Normally it just redraws once because that's what you normally want. But I put a loop around it so that for this demo, I can slow down our redraw because it makes it easier for me to time certain things. Okay, so what do we do when we redraw? We first check whether we're at high zoom or not. So we call that function. And let's go look at that function. So I go to that function. You see we get, again, a start time. And at the end, we call this profile CSV. And we're actually calling it with the wrong name because I changed this. So I'm going to change this name. So it's going to be check high zoom. Okay, and that's going to time this function. which just times, well, just checks whether we're zoomed in or not. We got this function, draw all features. Okay. So if I go look at it, this draw all features basically goes through all of the lakes, buildings, etc., the features, and it draws them, rivers, and so on. And it has a little bit of code to decide, are you really zoomed in or not? And it changes this drawing a little bit. And again, we get the start time. And at the end, we say, let's print out the time to that CSV file. And the time we're printing out is for draw all features. Okay, let's see. Whoops, let me get rid of that. Strange. Okay, you can see there's a bit of code that's not active that can draw intersections. So that's just for debugging. This routine is draw all segments. So what does that do? So if I go look at it, this basically draws all the streets. Okay, and it's got a little bit of it's got various code in there to decide how to draw different streets. And then at the end, we again call this profile CSV to record how much time do we spend in draw all segments. So draw all segments is our routine to draw streets. Okay, there's another function that we put that same code in for labeling, so putting text labels on points of interest. There's another one for putting labels or text on street names. Something that is not active in this version I'm going to show you, won't do anything useful, is traveling salesman, so it can visualize the milestone 4 algorithm. We can draw subway stations. Okay, so if I go look at this function, okay, we've got some code to draw subway stations, and again, we're timing it. We've got the start time, we passed in the start time, and this line is going to, well, we measured the start time at the start of the routine up here. So this line got us the start time. And then down at the bottom, we call our profile routine again. Okay, so, and that's it. Oops, let me go back one more. Okay, and then we basically also time the whole redraw routine. Okay, so we can have overlapping timers. So I've timed all the helper functions, every single one of them. And I'm also timing the whole routine draw, so I get the total. All right, let me compile this, and I'm going to compile it in release because I actually want to know how fast this is when when we're running our optimized code. I actually don't really care that much about how fast the debug code is. I care about how fast the release code is. So I just built it in release mode, and now I'm going to run it. Okay, so it's going through load map. And I see a question from Marco. Why don't we have the if-def inside the helper? Yeah, I should change that actually. So I'll move the if-def inside the helper function. Actually, that would be better. So it's because, yeah, I modified the slides after modifying some of the code. So the slides have a slightly cleaner style than the code because what Mark is asking is, why do I have this if-def here? Wouldn't it have been cleaner to have put it inside the helper function? And yeah, it would have been. And that's what I showed you on the slides. So right after this, I'll go and change that to make it a bit cleaner. Okay, so let me bring this back up. Oops. Okay. And see if I can get this window on the top. There it is. Okay, so there's my, my map. I'm going to turn on names. Okay, and I'm going to turn on subways, and then I'm going to zoom in. So every zoom in is going to do a redraw. So I'm zooming in, I'm going to move down a little bit. That's going to be a redraw. So I'm going to see in the CSV file, okay, now I basically have zoomed in enough that some extra buildings showed up. Now maybe I'll look around a little bit. Okay, and that's enough. I'm now going to hit proceed. So that's going to end my program. Okay, so I just ran my program with this profiling turned on. Now what I want to do is I'm going to open that up. So LibreOffice Calc is a spreadsheet. And I can basically go open. Let's see. And what did I call the function again? Funcperf.csv. Okay, so I just opened up the CSV file that we created. And we had a timer on load map. So our load map took about 7 seconds. So that takes a while. Then we have our first redraw. And the first redraw is here, all these functions. So we timed all the helper functions. So draw all features actually took quite a while, more than a quarter of a second, which for a redraw is significant. Drawing the street names, let me zoom in here a little bit. Maybe that'll make it easier to see. Okay, let's see, view, zoom. Let's see what 150% looks like. That's probably better. Okay, so drawing the features, well, the buildings, the lakes, the rivers, actually took quite a while. So it took about more than a quarter of a second. Drawing all the roads, so that's the street segments, was pretty fast, 100th of a second. I didn't actually label the POIs because I was zoomed out, so that was incredibly fast, like less than a millionth of a second. I didn't draw street names, so because I was zoomed out, so that was really fast. And Traveling Salesman is not active because we're not actually running the milestone 4 code, so that was really fast. And then the total time for draw, because remember I timed not just the helper functions, I timed the whole routine, was about 0.28 seconds. And that makes sense. It's pretty much the addition of all these helper functions. So then I get a second redraw, okay? So my second redraw is here. So that's when I zoomed in a bit. And this one's interesting because actually draw all features got quite a bit faster. So it went from about 0.27 seconds down to 0.04. So that's actually a lot faster. Draw all segments, so the streets is about the same, 100th of a second. All the other routines are about the same. The overall redraw was 0.05 seconds. So that means I could do 20 redraws a second. That's a lot better than I had the first time. There can be some transient CPU time issues due to, you're learning in ECE 243 how caches work and so on. Processors are pretty complicated. So, and the graphics code is kind of complicated. So I don't entirely know why this takes longer in the first redraw, but it's pretty consistent. I've run this many times and the first redraw is slower. It might be a caching effect, meaning data is being brought from off-chip into the on-chip caches, and then after that it's faster. It might be something with the low-level graphics library. But basically, I don't really care then too much about the first redraw. I care more about the second one because it's noticeably faster. And then as I keep zooming in, you'll notice it's relatively consistent. Okay, so draw all features took about 0.04 seconds, drawing all the roads took about 0.01, and everything else was kind of negligible, and my redraw was about 1/20th of a second. As I keep going down here, I'm basically zooming in more and more and more. So let's see what happens. At a certain point, as I zoom in, we show more detail. So let's go far down to where we're zoomed in a lot. And so quite a few redraws here as I zoomed in. When I'm zoomed in a lot, basically, if you remember what I was showing you on the map, we started drawing more buildings, whereas when we were zoomed out, we didn't show all those buildings. So that actually made draw all features slow down again. So now it's 0.28 seconds. Drawing all the roads also slowed down some because we drew more roads, but it's not as bad, about 0.04 seconds. Labeling the POIs, now we're drawing names on things. It took 3/100ths of a second. Labeling the roads took about 4/100ths of a second. And drawing the subways is still really fast, much faster than a millisecond. The overall draw time was about 0.4 seconds, which means we're only going to get 2.5 redraws per second, which is not fantastic. And then there's another redraw here, and you can see it's pretty much the same now that we're zoomed in. Okay, so by adding this code to my map, I can see where we spend time, and it changes a bit as we zoom in and out. And this tells me, actually quite a bit. So this tells me that if I want to optimize this, I need to work on draw all features. That's by far the slowest routine. Working on changing how I draw streets or how I label POIs and streets is not going to matter much. I got to work on draw all features. I don't quite know why it's slow, but it's the key point. So maybe now I would go in and put more timers. That's one thing I could do. But I'm going to show you some other techniques to try to zoom in on why is this slow. Okay, so let me go back here and see if I can quickly share my screen again. Okay, so okay, so those timers are really useful, but in order to use them, we have to know what code to measure. So how can we figure out what code we want to measure? Because we'd rather not write timers well, we could write timers all over the program, but that might take us a while. So a simple way to do what's called profiling the program, try to figure out where the time goes without changing the code, is what's called manual random sampling. So to do that, we run the debugger, and then we can stop it with this button. That's the pause button. We can look at the call stack. So we can go click on the call stack button, and we can see where are we. So in this particular case, we're in pushback, and pushback was called by draw segment, which was called by draw. So we can tell where are we. We write that down on a piece of paper or remember that, and then we hit this button, the continue button, to keep going. And we do that several times. And we see, are we always in the same routine, or we're 90% of the time we're in the same routine? If so, that's the routine you want to focus on. Go and look at that code in depth, or maybe insert some timers. Okay, so let me quickly demo that. So I'm going to switch back to the other screen. Okay, let me shrink down this. Shrink down this LibreOffice thing. Okay, so now I'm going to run. Usually you don't run the release build through the debugger because it's harder to figure out what's going on with the variables. But in this case, I actually am going to run the release build because I want the full speed code. And I don't really care very much about variables being optimized away or the code being changed a little bit. I just want to know what functions I'm in. Now, it's going to be hard for me to actually click fast enough on pause and continue. So what I'm going to do, see if I can go back to, that's not where I want to be. Okay, let's go back here. This is why I have this num redraws. Okay, so I'm going to change my num redraws to 30. By changing my num redraws to 30, I'm going to slow down my redraw function on purpose so that I can actually have a reasonable chance of clicking pause and continue a few times during a redraw and seeing where the time's going. All right, so now instead of clicking the arrow, green arrow just run, I'm going to click the debug arrow. Okay, so it's going to start debugging. I'm in load map right now, so I don't care about that right now. I'm not trying to optimize its speed. Okay, and now my graphics are alive. I'll just move it over here out of the way. Okay, and now I'm going to zoom in, and it's going to be slow because I made it actually redraw 30 times. So my redraws are going to be slow. I'm going to zoom in a couple times here. Maybe get down to where I get all the details. Here, I'm going to turn on subways. I'm going to turn on names. And I'm going to zoom in a bit more. And at some point, we're going to start seeing buildings, which is where it got really slow. Okay, so that may be now. So let's hit pause. So I hit pause, and I can hit the call. I can see where I am. So I pause, and I'm in draw segment. Okay, and I can look at the call stack. How did I get here? I'm in draw segment, which was called by this helper function, draw all segments. So I'm okay. So now I'm going to hit continue. I'm going to hit pause again. Where am I now? I'm still in draw segment. So it's taking a little while. Pause again. Okay, this is actually in the polling function. So poll means my program's back to waiting for me to do something. So I need to do something. Maybe I'll just hit this button to make a redraw again. I need to continue, and let's pause. Okay, so now I'm in draw feature. Okay, so I'm in draw feature, and it's deciding what kind of feature have I got. Let's do that again. Okay, I'm in draw line, and draw line was called by draw feature. So I'm drawing a line that is needed for some not closed feature. Do this again, pause. Okay, I'm in draw line, and draw line was called, I'm looking at the call stack down here, draw line was again called by draw feature, which was called by draw all features. So let's keep doing this a few more times. Okay, where am I now? I'm in a minimum function, and that minimum function was called by fill poly. Okay, so fill poly, which was called by draw feature. Okay, keep pausing and continuing a few times. And now I'm down in some vector manipulation, and the vector manipulation, let me make this a bit bigger. The vector manipulation was called by draw segment. Okay, so I can go see where. So I'm pushing some coordinates into, so I'm basically going through curve points and constructing some vector that I'm about to draw. Okay, pause a few more times. I'm back in draw. I'm back in fill poly. Fill poly was called by draw feature. Okay, let's pause and continue another one time or two and then stop. Okay, I'm in draw feature again, and draw feature called fill poly. So I'm just looking at the call stack here, and you're kind of looking for the functions you recognize. So what can I tell so far? I wound up in draw feature a lot. Sometimes I was in draw feature when it was drawing a polygon, so a closed feature. Sometimes I was in draw feature when it was drawing a line, so an open feature like a river. Sometimes I wound up in draw segments, and in draw segments, sometimes it was drawing lines, and sometimes it was manipulating a vector, like loading up all sorts of coordinates of curve points. And now I'll just let this keep going. Okay, and it's eventually going to bring back up the mapper, and it's waiting for my input. So I think I figured out enough, though. Okay, so by pausing and continuing multiple times, I can tell that polygon drawing and line drawing are a big deal, and I'm also manipulating a vector in draw segments, and those where I was spending my time. So I can go look more deeply at those things to see, is there anything I can do about it? Probably I want to try to draw fewer polygons and lines. That's probably because I kept winding up in fill poly and fill line inside the feature redrawing routine. That's probably what I have to do, is figure out, can I not call that so much? Okay, so let me stop that and go back here and share my screen again from the other terminal. Okay, so when you don't know where your time's going, it's going to be a pretty fast, pretty easy to use technique. So it's pause and continue technique. But if you want, you can only pause and continue so fast. I could maybe pause the program after half a second or a second. So I can't sample with very fine granularity. If I want to get more detailed measurements, I can use what's called a profiler. And to do that, we've set this up for you already. You compile using the profile configuration. So in NetBeans, you can just select this profile configuration and build it. Or if you're in the command line, you can go make configuration equals profile. You then run the exerciser with a -- profiler argument. You probably want to run it on, I'm going to run it on just the Toronto test case because I want it to run faster. So I'm going to run the Toronto test case with this profile option. And then we have a couple of visualizers, or we have a visualize tool called EC297 Profile Visualize. And the profiler, this command produces output in a file called perf data. So we tell that to this profile visualizer command. Okay, so let me quickly just show you what's going to come out of that. So the commands I just showed you, in the end, what it'll produce is a visualization of your program's runtime. It is showing you a graph, basically, of the program's runtime. The nodes are functions, and the edges, okay, so every one of these boxes is a function. That one, this one, and so on. And all the edges are call relationships. So that edge means this function called this function. And the colors, and more importantly, the numbers, I'm going to zoom in a second, tell you where did the time go. Okay, so this is zoomed in on a piece of that call graph. So the test case that I profiled is called Draw Toronto. So that's the name of the essentially program. So that's printed at the top of this box. Our redraw routine is called draw. So this is function draw. And in function draw, we spend 0% of the time actually in function draw. So draw doesn't do much. But if we include all the helper functions that it calls, we spend 74% of our time there. Now, what helper functions does it call? Well, 58% of our program's runtime goes to this helper function, draw all features. And you saw that when I was doing the pause and continue. The draw all features was a big problem. You also saw it when I put in the profiling information to a CSV, like when we put in manual timers. So the profiler agrees. Draw all features is taking 58% of our total runtime. And where does that time go? Some of it is drawing the features, some of it is getting the feature type. That's what it's telling us there. Also important, but not as important, 15% of the program's runtime is that draw all segments routine, which was drawing all the roads. And that took 15% of our time. And we could go down and see, well, where did that go? So we can go look at all this call graph in detail. All right. And I just told you that. I showed you all those things. There's another way you can visualize this. So the same program, after you've run after you run your mapper with profiling turned on, we can use this ECU 297 profile visualize tool again, but we'll pass it an argument -type flame graph, -t flame graph. And again, its input is this perf data file that our mapper produced when we compiled it with profiling and then ran it. So what does this flame graph look like? Let's see, I get rid of this text here. Okay. It's just another way to visualize who called whom and how much time did they take. Okay. So this is showing that our draw function, well, here's draw Toronto. This is the whole run here. And draw Toronto called a few different functions. So it called the translate function. That's when you click on the buttons to move the view left or right. It called the zoom in function. It called, and each of those called a function called canvas redraw. Okay. And canvas redraw called the function draw. So each one of these stacks is kind of the same. It's basically showing me here are different ways you got to your redraw function. But they all get into this important function called draw. Okay. And if you look inside draw, you can see that a lot of its time is in this draw all features routine. And the way you can see that is the width of the bar. So the width of each of these things represents how much time do you spend in it, and the stacking represents who called who. Okay, so this means draw called draw all features, and draw all features is most of the width of draw. Let me change my color here. Say that changes to green. So draw all features is most of the width of this draw recall. So that's where most of your time went in draw. And if you go look in these, you'll see, well, what does draw all features call, and how much time does each of those things take? Okay. If I double click on one of these bars, so I've double clicked on this draw bar so that I could zoom in on it, you can see more. So basically draw spends most of its time in draw all features, or calling draw all features, and some of its time calling draw segments, which is draw the roads. And then if we can see that draw all features spends a good chunk of time calling draw line and a good chunk of time calling draw poly, and a fair amount of time checking whether or not something's a closed feature. So if I want to optimize, these are places where I should go look. All right, in these routines. These calls up here are basically now inside, inside draw line. Okay, so I can't do much to optimize these because that's now inside the graphics library. So what I really want to do is figure out, why am I calling draw line so much? Maybe I can do less of that. And is there anything I can do to call fill poly less? Okay, so that is it for how you do profiling. Let me very quickly demo that. Okay, so I set the profile build. What the profile build does is it leaves most optimization on because we'd actually like to tell where our CPU time goes.
Vaughn, we can't see NetBeans.
Oops, sorry. Let me try sharing this. Thanks.
Yeah, no problem.
Okay, so in NetBeans or at the command line, I select the profile configuration. What does that configuration do? It leaves most optimization on because we really want to measure the time in our optimized code, but it turns off one optimization called function inlining that can basically paste the contents of one function inside of another. Because function inlining means some of your functions disappear, it makes it harder to interpret the output. So we turn that off. It affects your runtime a bit, but not too much, and it also generates extra information. So that's what profile does. Now I'm basically doing a clean and build. So this is building. It's going to take a minute. And once it's done, I'm just going to run it. I'm not going to run it through the debugger. I just want to run it. Okay. And I've left my my screen redrawing is still doing 30 redraws because I kind of want to optimize it. I don't want to spend forever clicking to make it redraw over and over again. So I've just left that so that I'm going to get more redraws quickly so that my redraw time is going to be dominant. And that's the main thing I'm going to see in these profiling output. Okay, so my map is drawn. I'm going to move it over to the side here. And now I'm just trying to essentially exercise the program. I'm going to turn on subways. I'm going to turn on names. And I'm going to zoom in a few times. And again, it's going to be a bit slow because I intentionally wrapped a loop around my redrawing. So it's actually redrawing 30 times each time. I don't have to do that, but basically I don't want to have my CPU time dominated by load map because I'm going to waste my time looking at all my top routines in terms of CPU time are going to be in load map, and I don't care about load map right now. So I basically want to use a bunch of CPU time with a whole bunch of redraws so that I can get information that's more relevant to me. Okay, so I basically got this drawing a few times, and I'm going to stop shortly because that's probably enough. Okay, and then I'll hit proceed to end the program. I'm getting slightly bored of waiting for this. Okay, it's because I slowed my redraws down a lot, so I'm just going to end it. And let's go out to the command line. Okay, so there's this perf data file. Okay, and it's pretty big. And let's see, ls-l. There's another one that I generated last night. And I'm going to move the one that I generated last night because I ran that for a bit longer. So it might be a slightly better version. So I'm going to just use that as my perf data. And the command to see this is ECU297 profile visualize. And then the name of that I'm going to use for my data is perf data. And this is now going to bring up a visualization of the call graph, just like I showed you. And it can take a minute. There's a fair amount of data in here. Yeah, you don't need those move commands. I basically just it generated perf.data for me, and because I have one from last night that I clicked around a little more, and I know I've already looked at the data, I'm just using the one I generated from last night. So you don't really need to do that move command, and I probably should have just run the other. I could have just specified the other data file. Um, I'm gonna post a quick start guide on profiling as well, so you're gonna get some more information on this. Okay, so here's the call graph, and I'm gonna hit Shift plus to zoom in a bit. So I'm just zooming in a little so you can actually see more. And now let's go look around this call graph. Okay, so what is this telling me? Um, Basically saying the unit test framework started your program up, and load map took 5% of my time because I ran the graphics for a while last night. And here's where load map spent its time. I don't care. So I don't want to look at that part. I'm not optimizing load map. It also says, well, draw map took a long time. Draw map took 78% of my time because I did spend a while running the graphics last night. And what did it call? Well, it called this application run. That's an EasyGL function to create the window. That's where pretty much all of its time went. And that goes through a couple of other functions. I don't really care about that. Basically, this gets down to draw Toronto. Okay, so draw Toronto is my screen, or sorry, my EasyGL canvas redraw here is where a whole bunch of stuff comes together. It's basically, this is my main redrawing function. Okay, and that's what EasyGL is calling to redraw the screen, and it calls my draw function, which does all the work. Okay, so almost all my time, 93%, is in redrawing the screen. And how does that break down? Well, 75% of my total time is drawing features. And if I trace down where does that go, well, most of it is just going into draw feature because there's a big loop inside there. So 69% of my total runtime. And that breaks down into a little bit of time, 4% to get the type of feature, another 4% or 5% to get the feature points, 18% to actually fill in polygons, so closed features, quite a bit of time to check if it's a closed feature or not. So this is the helper function. I spend 10% of my time checking if it's a closed feature or not, and 35% of my time drawing lines. Okay, so what does this tell me? The drawing lines is interesting. I'm drawing all these rivers and stuff. That's actually taking a long time. I'm probably wasting some time here checking is closed feature. I could probably do better than that. And I'm spending a bunch of time drawing polygons. So it tells me what I should do to go optimize. And I can go further down into this and see what's going on. The other place my draw function is going is draw all segments. That's drawing my streets. Not as big a deal, 15% of my time. Draw subway stations is small, 2%. So I got to optimize draw all features first, and then maybe I could optimize draw all segments, or maybe not. And there's basically nothing else. Like any other code refactoring I do is just a waste of time from a point of view of speed. And you can see, you can just kind of keep diving down into the details of this. This tells me when I draw streets that some of it is some time is spent converting from longitude and latitude to X and Y, but not that much, and so on. But my big problem is over here. And this is spread across the drawing of polygons, drawing of lines, and figuring out if it's a closed feature. So that's where I would go to optimize more. Hopefully that makes sense to you. And like I said, I'll post a quick start guide that explains this. So let me close that up. And in the last moment, let's see if I can show you a flame graph. Okay, so that's the normal way, or the default way, to visualize one of these profiling outputs. If I specify -t flame graph, I get that alternative visualization. It's processing the same data, this perf.data file, but now it's just going to show me the output in a different way. Okay, this again is going to take a moment to run. Okay, and this is the flame graphs that I showed you in the slides. So this says the whole test is draw Toronto. That's all my CPU time. And all of these big bars are basically different kinds of redraws. Redraws due to zoom in, redraws due to shifting over. So let's just pick one of them. Let's pick this redraw type. It spends almost all its time in this draw function, which is my screen redrawing. And you can see most of the times in draw all features. And some of it is also in draw the roads, draw segments. And inside draw all features, almost all the time is inside this draw feature helper routine. And it breaks down into some time on draw line, some on draw on fill poly, and some on is closed feature. So this representation doesn't represent, basically vertical means who calls whom. So draw called draw all features, which called draw feature, which called is closed feature. And width represents how important it is in terms of CPU time. So it's going to be an alternative way to visualize. If I click this reset zoom, I'll zoom back out. Okay, so that is the end of the tutorial for today. Let's see if I can get zoom back. Okay, if there are any questions, we don't have much time, so we're going to go to repeat the tutorial if there are people around who want to see it repeated. But if you've got any questions, just type them in the chat right now.